Okay, then, hello all. Welcome to AC's cases on harmonic analysis and gravitational lensing by Srinidhi Bhatt. Uh, so, please keep your questions to the end of the talk. So, we'll have a Q&A session so that you don't interrupt the speaker. We request you to keep your mics and videos off so that we don't crowd the bandwidth. Please note that this session will be recorded and uploaded on YouTube on AAC's channel. So if your friends or someone has missed it or is interested, you can tell them to watch it over on AAC's channel. Don't forget to like, share, subscribe, and hit the bell icon for more updates. Without further ado, just Srinidhi.
Yes. Good evening, everyone. I'm CMD Bhatt. I'm a student in electronics and communication engineering, but I'm a person more inclined towards math and its applications. So here we are today, exploring a little about gravitational lensing, and we are going to focus more on how we are coming up with a solution with, I mean, a small solution to this problem, or which you're going to see in the near future. So let's get right ahead to the beginning. So basically, yeah, we'll be dealing with some of the math in the first some 15 to 20 minutes. So firstly, we'll see what fundamental theorem of algebra is. So fundamental theorem of algebra basically says if you have any complex number of degree n, it has precisely n complex roots. So you may say like this looks like a very trivial result. Like if you take any n degree complex number, you can say like, I mean, of course, why not? There must be n complex roots, but it actually is not. Like if you see in a real polynomial equation, what do we say is the graph may not even intersect the real line, and there we define the notion of complex numbers. Like even a simple equation called x square plus 1 equal to 0 has a complex root, and it does not have a root in real domain. So which clearly says that this result is something which is not so trivial. But yeah, but still this holds, and this has been proved over course of like 30 to 40 years. Like in the first published proof was by C.F. Gauss and D'Alembert of this conjecture. So, but there were many flaws in this conjecture, because the basics of complex numbers and complex analysis were not so much developed so as to get the idea of a complex root in a complex polynomial in a clear fashion. So Gauss later later in his years, he published 3 correct proofs of the same theorem. So now there are like numerous approaches to prove this theorem. Just to give a small idea of how to prove this theorem. So one of the properties of complex analysis says that if you like any complex polynomial of degree n, as you go over infinity, you can basically equate it to a naught z power n, if you assume it as a naught z power n plus a1 z power n minus 1 and so on. The smaller powers vanishes comparatively if you take like z power n. So you can just equate it almost to z power n. It's like z power n can be like something like I mean, you can call it as some upper bound, lower bound. So from there, that's a property which says that if you can equate it to z power n, the number of roots of z power n will be same as number of roots of the polynomial. So this is one of the notions. So this property of where number of roots of polynomial and number of roots of z power n or some very trivial polynomial took a lot of time to develop. So this was a very hard concept for people in 1700s were able to understand. So, but today we sit here and just see it as a very trivial result. Moving on, so what is harmonic analysis? So basically, harmonic analysis is just analysis of functions or polynomials which are harmonic. So as the name says, it's harmonic analysis. So what are harmonic functions or harmonic polynomials? So harmonic functions basically satisfy the Laplace equations as shown here. If h is some polynomial or a function, then del h equal to 0 is what basically a harmonic function is. So this simple equation has so many applications, has opened a whole branch called harmonic analysis. So that's the depth of a that's like the depth of one equation. Like an equation with, I mean, if a function just satisfies those equations, it opens to a huge door where it satisfies a lots of properties. This acclaimed to be one of the hardest fields of analysis in mathematics. So just to give you a small glimpse of this field, some of the applications of this are basically this is like extensively used in astrophysics too. So as you can see, that's a Laplace equation, that's del h equal to 0, which you use it a lot in astrophysics. And so it is like a basic tool which helps you find the Laplacian on the domain, on lots of manifolds and all the other graphs. So yeah, so from this equation, where we go is we take a simple complex linear change of variables to bring it into a easier way so that we can easily analyze it or understand it. So yeah, so any complex polynomial can be written in the form of p of z minus q of z whole transpose, a whole complement. So p of z and q of z are two different polynomials of complex number. And you may say, like, if q of z is just a polynomial of a complex number, then how will q of z whole bar makes a difference? Like, just an addition of z bar equal to x minus I, the idea of conjugation varies. So basically, when you learn a little in the complex analysis, you will see that a function satisfying or a function being derivative of, I mean, a differentiable with respect to z bar is such a strong condition that it just makes the function not at all derivable, or it is also called as analytic. So what is the idea of analytic is, you take a function, and in a normal, what we learned in +1 +2 or our 11th and 12th is, we take a function, we take any polynomial, or any function, we can just differentiate it if it's continuous. That's the idea behind the normal one-dimensional differentiation, like the one-dimensional differentiation. But in complex functions, you almost deal with 4 dimensions. It's like mapping a 2-dimension into a 2-dimension. So it's a little difficult to imagine, but if a function can be differentiated with respect to z bar, then it is not analytic in the whole plane. So yeah, that's an idea which, I mean, that's, if you explore in that idea, you go into lots of other different details about that in a different domain. So we are not going over there. So let's just cut to the chase, where we take p of z and q of z as simple polynomials. So one example is h of z equal to z power n minus z power n whole bar. So this polynomial is said to have infinite number of zeros. So it is almost kind of a trivial, because if you take z power n minus z power n whole transpose, it is like the zeros almost lie around parallelly around the origin. So all the lines which are almost parallelly around the origin satisfies this equation. So moving on, so harmonic polynomials and WILMSHURST'S conjuncture. So yeah, basically what a conjuncture is conjecture is a conclusion or proposition which is suspected to be true, but due to some it is suspected to be true because of some preliminary supporting evidence, but a proof, like a solid proof, is not been yet established. So yeah, where are we going with this conjuncture? Yeah, you will see that in 5 more minutes. So yeah, let's take the h of z, which we defined as p of z minus q of z whole transpose. So if we take h of z, then divide it into real and imaginary parts, and we take the degree of real part as m, degree of imaginary part as n, then we have some interesting results, which has been, some has been proved and some is still yet to be proved. So the first important theorem which we need to focus as a build up to gravitational lensing is basically this theorem 1, which says if the degree of if the harmonic polynomial of degree n satisfies an equation such that limit as n tending to infinity mod h of z equal to infinity, then h has a maximum of n square zeros. So the number of zeros, the like upper bound on the number of zeros is a very strong condition which gives a lot of wonderful results and has a lot of applications. So yeah, and one more, the theorem 2, which was proved, it was a conjuncture which was proved until very recently. It says, so basically this set hash of means the number of so number of z which satisfies the equation p of z minus z bar equal to 0, where n, that is the degree of p of z, is greater than 1, is always less than 3n minus 2. So yeah, due to the complexity of the proof of this theorem, it's not so easy to go through the proof and tell you how this upper bound is attained. So we'll skip that a little and yeah, we'll move ahead. So yeah, after we get this result, the obvious question would be, we take p of z and q of z as normal polynomials. So what if we can extend this to rational polynomials or rational harmonic functions? So do we get an upper bound on number of zeros? So it turns out that an astrophysicist, S.H. Ree, studied this and while working on the gravitational lensing field, and so she arrived at a conjuncture that if degree of r, so we take r equal to p of q by p of z by q of z, where p and q are, as we have seen earlier, p and q are complex polynomial functions. And so when we take degree of r as maximum of these two degrees, and we take a harmonic polynomial equation r of z minus z bar, then the number of zeros that this attains is always less than 5n minus 5. So you can see how, like, this is just a constant on number of zeros of a polynomial. So how can something like a constant on number of zeros of a polynomial have an impact on a topic of astrophysics? Yeah, so before we go ahead with gravitational lensing, let's take a small detour into what's called cosmic distance ladder. Yeah, if you're not so into math and if you're a astrophysics enthusiast, this might be an interesting topic. So what is a cosmic distance ladder? So basically, since olden days, we were always wondering about the radius of the Earth, or radius. I mean, radius of Moon, radius of Sun, or distance from Earth to Moon, Earth to Sun, or distance from Earth to any planet that may be, any planet which we see from here, or any star which we see from here. This so basically these distances form something called a cosmic distance ladder. So the distances which we wonder about is too far to measure, so we do it indirectly. This is one of the beautiful phenomenon which can clearly explain how science, math, and lots of other reasoning can lead you into something very meaningful. So basically, it all started in the very old days of Aristotle. So yeah, let's go a level by level. So in the first rung, which is the radius of Earth, and radius of Earth, came Aristotle. So what Aristotle saw first was shadow of Earth on Moon is always circular. If you see shadow of Earth, I mean, they obviously knew about Sun, Earth, and the Moon, and sun's light, which is shadowed by Earth, will light the Moon, and that's how we see a moon lit up. So yeah, so Aristotle saw that shadow of Earth on Moon is always circular arc. It was always a circular arc, no matter which day it is. So this for all those flat earthers out there, if Earth was not a sphere, then this phenomenon is not possible at all. If Earth was just a disk, if you yeah just a disk, imagine a disk, and you try to put a light source, not onto the not directly onto the surface, but a little at an angle away from the surface, then you will clearly see the shadow will be something like elliptical. So, but what we saw in case of Earth and Moon was the shadow was always circular arc. So yeah, Aristotle saw this, and he was one of the first people who, in ancient times, without any much technology, told that Earth is spherical. But after that, Eratosthenes, one more person, found out the radius of the Earth with such with such less technology. Like the technology, you can imagine the technology during 200 BCs. So he computed the radius of Earth with 8% accuracy just by looking at the sun indirectly. Of course, like you can't just look at the sun directly and say the radius of the Earth, but yeah. So what he saw that was, he found the angle of he saw that as the during how do I put it? Yes, as the light from sun was, he found the angle of deviation of sun and the reflection, and it was a simple math where you could just use the property of two similar triangles and find the radius of Earth. Yeah, I'm really sorry I could not go through the pictorial representation of each, as this is not the main topic. This is like a story 2000 years old, which is still going on. The second rung comes the moon. So yeah, we'll just brush through each rung a little rapidly. The second rung comes moon. So how did we find the radius and distance of moon from Earth? Basically, Aristarchus was a person who came after Aristotle. He knew about Aristotle, and he surprisingly found the radius of moon with a very high accuracy of almost 10%. So what he saw was, he saw during an eclipse, the amount of the time where moon was exactly eclipsed must be 2 times the radius of Earth. So he knew the radius of Earth, and he saw the time which moon takes to 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 cross a distance of two times the radius of Earth, and it took 24 hours to circle an Earth. That's how, I mean, yeah, that's a fact. We know that, right? So from that, he found out the distance from Earth to the moon with a very high precision, and also he found out the radius of the moon by just the phenomenon of moon setting. So moon takes almost like 2 minutes to set. So the 2 minutes and 2 times the radius of moon, and it takes 24 hours again to circle. So this was simple math, but the technology to observe these things, there weren't even telescopes to find this. So it was very surprising, these results. Then we go to Earth, Sun. So this sun, the distance of sun relied on moon. So basically a lunar eclipse almost covered the sun completely. This was very surprising for them, because they thought sun is that small. I mean, if you see in the sky, sun is very small. I mean, in the ancient times it was very small. Earth is very big. So the fact that sun is way bigger than Earth was very surprising for them. So yeah, it is a very trivial result when when a solar eclipse, a moon completely covers the sun. So the ratio of radius of moon to the distance of moon, and the ratio of radius of distance of Earth to sun, and the radius of sun are same. So from that, he same Aristarchus saw this and told that sun is way bigger than Earth, so it is absurd to say that the solar system is geocentric, which was the notion back then. So of course you may say it was not Aristarchus, it was Copernicus which proved that we have a heliocentric solar system. But yeah, if you see Copernicus paper, he credits this in his acknowledgement to Aristarchus. Next comes planets. So this was seen by Copernicus, and then came Tycho Brahe, who went to an island and collected a lot of points of lot of planets, like lot of data regarding lot of planets, and tried to come up with the distance. But he could not come to a very high accuracy. So Kepler, it was an easy thing for Kepler, as he had all the data from Tycho Brahe, and he just used his data, and could come up with a very good accurate results. Then comes the speed of light. So why speed of light is here? Because finding the speed of light was a major change, as we know, even the electromagnetic waves travel in the speed of light. So this was a huge thing for the astrophysics. So Galileo was the first person to try to find the speed of light by just, yeah, it's not a very accurate answer, because what he tried to do was normally how much a light takes from one place to another. But because the speed of light is so fast, it's a little difficult with the technology they had back then. So then comes nearby stars. So the nearest, they tried parallax method, which is a little famous, as you all might have heard that. It's looking from one position, and you go to another position and look at the same thing. You see a parallax, and from that you try to find the distance. So these are all the indirect approaches we had. And the next one comes the Milky Way galaxy. So now the technology has advanced so much that we use techniques like spectroscopy and a lot of other main sequence fitting. These are some of the techniques which are used to find the distances. And then comes Cepheids. So Cepheids are basically stars which have varied which emit very type of lights. So yeah, so this cosmic distance ladder is an idea which has extended since 2000 years, and today we are trying to make a map of our whole universe, which you can see developed from a simple fact which Aristotle saw 2000 years ago, that the the phenomenon of eclipses and sunset and sunrise. Yeah, let's finally come to the topic of gravitational lensing. So what gravitational lensing is when you see a distance light source and an observer, of course it's a space, so there are lots of other objects in between those two objects, like an observer and a light source. So what happens is, when we try to observe this light source, because there's a bending of light from the source as the light travels towards these objects, we see lots of different images of this light source. We don't see it at a single point. So that phenomenon is called gravitational lensing. So when I just introduce this topic, you may say, how is this in any way related to harmonic analysis, which you saw like 10 minutes ago? So yeah, it's a wonderful thing. You just say it in a couple of minutes. So nowadays this is like very useful to find distance objects in the universe, and also determine the mass of these objects by looking at the intensity of the light and the distance and lots of other things. So yeah, again coming to a little math, we have something called a lens equation in gravitational lensing. So what is a lens equation? That's in the right corner you can see a small picture where that's a light source and that's a lens plane. Lens plane is basically any object that is in between, which obstruct your vision directly on that source of light. So when the light emanating from that source bends through it, we can see two reflections on 2 points, say S1 and F2. So this happens a lot of, this is a very common phenomenon. This was studied a lot, and hence the complete field named after it, called gravitational lensing. So what lens equation does is, it basically assumes the observer and the particle and the source plane all to be in a coplanar, like all to be in the same plane. So when it's all in the same plane, it's a two-dimensional plane, so you can assign each point a complex number. Depending on the position, you can assign a complex number. So this is where if you see, this is where the dots are getting connected. So what we do is we project each mass to the lens plane. Lens plane is basically the line where our object obstructing our vision is present. So when we do that and just see that when we do that and try to see that try to do the vector addition across the triangle, or to be more accurate. So like if you connect the point in the lens plane and the source and the observer, you get almost a triangle. So that triangle, you can apply the vector addition property. If you know the notion that every point in a complex plane is also a vector. So on doing that and applying some weights to each of the reflections, because the reflections are through different pathways, so some may be dim and some may be dark. So we apply some weights to each of that and come up with a beautiful equation, which is W equal to Z minus summation J equal to 1 to N sigma J by Z bar minus ZJ bar. So what sigma J is basically a weight which is related to the mass of jth point. So if there are n masses which are in between the observer and the source of light, and you take a jth point, the amount of light bending on a higher a matter with a higher mass is more than a matter with a lower mass. So we apply this weight and we get this beautiful equation. So this is basically, as you have seen earlier, is kind of similar to a harmonic polynomial equation, rational harmonic polynomial equation. So if Z satisfies this lens equation for a given value of W, our gravitational lens should automatically map the position of, will map Z to the position of W in the source plane. So those tedious calculations or tedious math which we saw a little earlier about the harmonic analysis breaks down to the solution of this equation. So the number of zeros basically gives you the number of reflections. So yeah, that's the beauty of math applied here. So we see that the number of lensed images depends on the relative positions of the observer, lens, and source. Yeah. So one of the nice things which you can observe here is if the observer, lens, or the object and the source are in straight line, then the object has to completely obstruct the source. And this was studied by Einstein. This was studied, and it's a famous thing called Einstein ring, which was seen by Hubble telescopes. You can find lots of images on Google regarding this. So which finally brings back to our theorem 3, which said the number of solutions are less than phi n minus phi. So here we see that the number of lensed images by n mass planar lens. So yeah, we have assumed it's a coplanar. So of course it must be a planar lens with zero shear. It cannot exceed phi n minus 1, and this bound is very much sharp, like it's almost an exact bound. So which is, I mean, from this it's a little trivial that when n is odd, the number of images must be even, and when n is even, the number of images must be odd. So it also works vice versa. So for every n greater than 1, there exists a rational harmonic function which has exactly phi n minus phi distinct roots. So if you see some phi n minus phi number of images, then you can find a rational harmonic function of degree n which can satisfy, which can give you the exact point of that light source. So this is the basic idea behind the gravitational lensing. So this was studied by the same scientist which we saw gave theorem 3, SH3. So yeah, from this, where are we going with this? So this can be applied to a lot of spherically symmetric mass distributions in the lens plane. So we saw there's a lot of generalization here. Like we assume that the source, observer, and the lens are in the same plane, and all the obstructions which we see are also spherically symmetric. They are spherically symmetric mass distributions. So which is a very strict generalization. I mean, which is a very strict generalization. It does not apply to everything. So in a real case, how many lensed images can an arbitrary mass distribution produce? These are some of the questions which arose from these facts. And also, when an n lens consists of point masses which cannot be treated as coplanar, so then what is the upper bound of number of possible images? These are some of the questions, and these are still being worked upon these days. So this is one of the, as you can say, one of the very interesting field in astrophysics, which is very much alive till date. So yeah, what gravitational lens does is you can focus a light so that important properties such as distance and composition, rigid composition of the mass of the source of light can be found, and also the amount of light that bends around that obstruction can also be found, which can give you some information about that object's mass. So yeah, so looking at all this, we see how some abstract concept like harmonic analysis and complex analysis and a fundamental theorem of algebra, which just says polynomial must have of degree n must have n roots. So these simple facts, which lead to some very beautiful results, which can almost give you a location of a source of light, is one of the, yeah, as you can see, it's one of the very wonderful ideas. So yeah, I would like to end my session here by saying any topic in astrophysics you may take, it has a very nice and beautiful history behind it, which has developed into such a wonderful topic which it is today, and which we as a members of ASC try to find that, like, we being enthusiasts in astrophysics and astronomy really appreciate those facts. So yeah, thank you.